In the last video, I talked about how Philip Lenard did these experiments and observed that as the frequency of light is increased, there would be a current that flows through this circuit, suggesting that electrons get emitted by this metal plate, and it must be the energy from the light that ejects electrons from the surface. So you need a certain amount of energy to eject the electrons. And he observed that below a certain frequency, no electron is emitted no matter how strong the light is. Apart from this observation, he made another observation, which is about the kinetic energy. So suppose that there are these electrons coming out from the metal plate and traveling towards this other plate. So this is the positive side and that's the negative side. Okay. So from now on, I'll try getting used to calling this plate, this metal from which electrons come out, I'll try getting used to calling it a cathode, and the other side would be anode. So cathode is the place where electrons comes out. Okay, so these electrons that are emitted would move at a certain they would come out with a certain kinetic energy, and they would then be accelerated and they will be accelerated towards the positive pole, and the kinetic energy would increase. Suppose that we are interested in the kinetic energy of these electrons when it just come out of this cathode, right? When it just comes out of this cathode, there's a way to actually measure it. There's a way to do it, and it's quite a clever way. The way is to turn this battery around. Now let's see what we can do with this. Turn this battery around. I would instead put let's see, a negative pole on this side, a positive pole on this side. So this side I make it positive, this side I make it negative. So that becomes an anode. Well, that becomes a positive pole, and this becomes a negative pole. But if I do this, the electrons ejected would slow down, right? And that's the whole point. The idea is to increase this voltage until no electrons reach this side, and that means that this reverse potential will stop the electrons with the highest kinetic energy. And we would expect that if there is more kinetic energy, if the electrons come out with bigger kinetic energy, we would need a bigger reverse voltage to stop the most energetic electrons. Okay, so just by turning up this voltage and observing when the current falls to zero, we can actually measure the kinetic energy of the electrons. Right, and the relation is quite simple. All we need is to say that, right, let's say the reverse potential is normally written as Vs for stopping potential, Now this is actually directly related to the kinetic energy. We'll look at the relation in more detail afterwards. So the bigger the kinetic energy of the electron, the bigger the reverse voltage. So therefore, just by observing the voltage needed to stop the current, we can tell how big the kinetic energy is. So Leonard made this observation for different colors, right? And of course, when the frequency was below threshold, below green color, there's no current, so no stopping potential to observe. But the moment it used green light for this sodium metal, there is a current, so that the electrons are ejected with some kinetic energy. So you needed some reverse potential to stop it. Okay, so we found that you need some potential. It's not just zero. So this, we can either say that you don't need a stopping potential, or it's just zero. Now, for blue light, as you increase the frequency of the light, we found that you need a bigger potential to stop the electrons, to stop the current. And as you go to even higher frequency, like violet light, you need an even bigger voltage to stop it. And this clearly suggests that as the frequency increases, the kinetic energy of the electrons, of the ejected electrons, increase. But the even more surprising bit was that if, for example, when he used green light and he found that he needs maybe a small voltage to stop the electrons, the surprising thing was that if he increased the brightness of the green light, stopping potential stays the same. And that means that no matter how bright the green light is, the electrons are ejected with the same kinetic energy. The kinetic energy of the electrons cannot increase just because you increase the brightness of the light. The only way to increase the kinetic energy is to increase the frequency of the light. And that's another thing which is very difficult to understand at that time. So let me summarize this part of the results on kinetic energy. So the result is kinetic energy of the ejected, I'll just call it emitted electrons increases with frequency. Okay, so that's one important observation. The next observation was that for the same frequency, the kinetic energy stays the same, right? No matter how bright the light is. And that's very difficult to understand. Why doesn't it take up more energy if the light is brighter. Now, and in order to explain this, a few years after Leonard's experiments, in fact, maybe just about 3 years, Albert Einstein had the explanation. So this was in the year 1905. Albert Einstein. Now, Einstein's explanation that he proposed at that time is this: that the light energy coming in, the light wave coming in, is actually happens in, if you like, we can almost say that it actually happens in little particles, right? That means instead of our usual picture of a wave, a continuous wave of the light, like ripples on the surface of water, or waves traveling along over a very long string, Einstein imagined that instead of waves of light coming in, the light actually behave as if they are particles, like electrons, or like little stones on little ball bearings, little balls. These energies are sort of contained inside these little packets, and which we call a photon. So a photon. So these are the name for the little packets of light energy. And each electron, at any one time, each electron is only likely to absorb the energy of one photon. It may absorb two perhaps, but that must be extremely unlikely. And so that's the first point. That's the first idea from Einstein, that the light are in these packets, or if you like, the lights are like particles, right? They occur in packets of energy, and today we call it a photon. And next thing, in order to explain these results more quantitatively, you need to relate this to the photon energy to the frequency. So the idea is that the energy of a photon, right? A photon energy, according to Einstein, it depends only on the frequency. Depends only on the frequency of light. And he proposed that the higher the frequency, the more energy a photon would have. Okay, and the exact relation which he used was that the frequency, the photon energy must be equal to the frequency times Planck's constant times h. Okay, h is a very small number. I'll talk more about that afterwards. So anyway, the main idea is that the photon energy is proportional to the frequency. So this can actually explain at least the qualitative observation quite nicely. For example, why is there no current below a certain frequency? And the answer is that below a certain frequency, the energy of each photon is simply too small, simply not enough to for the electron to jump out of the surface, because in order it's reasonable to expect that in order for the electrons to jump out, we need to give it some energy. Okay, because they are bound, they are attracted by the protons in their own atoms. So we need to give it some energy. So if the frequency is too low, the energy of each photon would be too small to eject the electrons, to overcome that energy, which is called the work function. So that's why if the energy is too small, there's not enough energy to overcome the surface attraction, no electrons will come out. And it really doesn't matter how bright the light is. Right? A very bright light, say a very bright yellow light, in this example where we use sodium, just means that there would be lots more photons every second coming in, but each photon will still not have enough energy to eject the electron. And the electron would not just wait around, it would not just absorb the energy of one photon and then keep it there and then wait around for another photon to come in to eject it, so that meaning that the electron cannot just wait around and collect together the energy from a few photons until it has enough energy to get ejected. The reason is simply because when if an electron absorbs one photon energy and it's not enough for it to get emitted, it would bounce around. Right? Likelihood is that it would bounce around the other electrons or atoms and lose energy before it has the chance to absorb another photon again. So as long as a single photon does not give it enough energy to get emitted, the electron will quickly lose that energy before it can pick up another photon energy. Imagine that the photons, relative to the sizes of the electrons, we might imagine that forget that. So that would be the reason, because it's very unlikely for the electron to absorb two photons at the same time. So for this reason, it is possible to explain why below a certain frequency, no electrons can be emitted, simply because each photon does not give the electron enough energy to come out of the surface. And about the stopping potential, about why it does not depend on the brightness. Remember that for the same frequency, the kinetic energy of the ejected electron is the same no matter how bright the light is. And we can understand it using the same reason, because no matter how bright the light is, each photon has the same energy for that frequency. So the ejected electrons would always have the same kinetic energy, because you can only ever just absorb a single photon, even if the light is very bright and there are loads of photons. You can only absorb one. And that, in a very simple way, explained Lenard's observation. But that was not the only thing that Einstein's theory here can do. Einstein was able to make an equation, a photoelectric effect equation, from his idea, which can actually be measured and checked quantitatively.